Good evening, Lamai. Last day we had discussed about, actually we had started the discussion about the secondary interactions. Alright, and there we had discussed about the first 4 types of secondary interactions. Right, ion dipole interactions, dipole interactions. There we had discussed extensively about the hydrogen bonds. Then we had moved to dipole induced dipole interactions and as well as the ion induced dipole interactions. Right? Today we are going to discuss about the 5th kind, the London forces or London dispersion forces. Today our discussion is about that. Right. What are these forces? What are these London forces? Let's discuss. Actually, London forces are the reason for connecting the non-polar molecules. Connecting the non-polar particles together, London forces are the ones which are responsible. See, right? You know that if you take some argon, right, which is a noble gas. If you think of the connectivity or the attractions between the 2 argon atoms, right, that is all because of London forces. Right? How come? So the argon molecules will attract via London forces. Right? Like this. So what happens is this, Lamai. When one argon molecule or one argon atom come closer to the other argon atom, right? So electron density of this argon will repel due to the presence of electron density of the other argon. The negative things will repel now. So the electron density of this thing will repel, go towards here due to the presence of electron density here. So that some positive nature, less electron density will appear here, while some great electron density will appear here. Like that, then what will happen? To that positive pole, the electron density of the other argon molecule will attract. To that so produced positive pole, the electron density of the other argon particle or the atom will attract. So that kind of a negative delta will be created there, the positive delta here. So that the attraction between these 2 opposite signs is referred to as the London forces or London force. Right? These London forces happens between non-polar molecules. So this is a non-polar molecule, right? Or the non-polar species, right? Non-polar species, symmetric electron density. Initially, this is also non-polar, some symmetric electron density. But when those guys are coming closer to each other, some poles will induce, and then those will attract to each other. That is how the London forces are to form. Right? Not only with these guys, let's come up with some other examples. Not only the atoms like this, but also molecules like O2. If you think of the O2 molecule, O2. If you are with O2, that O2 is with a symmetric electron density. Symmetric electron density. Right? Symmetric electron density with the O2. What happens when another O2 particle, another O2 molecule comes closer to this O2 molecule? Right? So basically, electron density of this thing will repel from the electron density of the other O2 molecule. So that ultimately the electron density of first O2 molecule becomes like this. Right? The idea is clear, no? The electron density here will repel from the electron density here, so that you will ultimately end up with a less electron density here, while you are with a greater electron density here, greater negative nature here with some less negative nature here. So less negative nature means it is carrying the positive pole, while this one carries the other pole is your negative pole, right? So towards this positive pole, this guy's electron density will attract, so that it will create some two poles as well. It will create some dipole as well. Here the negative pole and here the positive pole. So attraction between these induced dipoles are referred to as the London force. This is how the London forces appear due to the induced dipoles. Right? So the interactions between these induced dipoles are known as London forces. Right? Actually, these are known as induced dipoles. Why we are saying so? Basically, in the presence of the other particle, the other substance, these poles are induced. Originally, those are non-polar species. Originally, those are non-polar species. Non-polar species. So, in the presence of the other particles, other outer electron densities, outer charges, these poles were induced. These poles were induced in the presence of outer charges, right? So that is why these things are referred to as induced dipoles. So the interactions between induced dipoles are referred to as the London forces. Not only the non-polar atoms, not only the elemental molecules like this, but also non-polar compounds also can come up with London forces. See, if you think of CCl4, CCl4 is kind of a non-polar species. CCl4 is kind of a non-polar species. See, some symmetric electron density with a CCl4, right? So CCl4 molecules are non-polar. These are perfect shapes, no? You know, the perfect shapes are non-polar, right? Perfect shapes are non-polar. What happens when these guys come closer to each other? Basically, the electron density of this thing will repel from the electron density of this thing, so that the electrons will go towards this corner, so that you will get some greater electron density here, making it a minus delta, and some less electron density here, making it the positive pole, the positive delta. So you would see the situation like this. The CCl4, right? And then the other molecule, this thing will also attract towards the positive pole of the species, so that you will ultimately end up like this, right? So that will also create some two poles. So ultimately these poles will attract the other London forces. Right? London forces are actually referred to as the induced dipole interactions, right? So these are some examples where you can see the appearance of London forces, right now. Okay, so you have got some idea about these second interactions, the London forces, right? right? Induced dipoles may create via two methods. Let's discuss about those two methods. The method number one. Right? The method number one. The idea is this. So basically, right? If you have to take some non-polar or any kind of a chemical species which are with electrons, right? So the chemical species are with electrons, right? These are the electron density, right? So there could be an instance where more of the electrons appear at one side, because these electrons are highly moving particles. No, electrons are not still. No, those guys are moving. So there could be an instance where you have, right, some great electron density at one side and some lesser electron density at other side. Some less electron density appears at this portion and some great electron density appears at this portion. So that kind of a instance could happen. Right? Then what will happen? Then we could say this area is with some more electron density and the other area is with some less electron density. That means you will create some negative pole here and positive pole here. Not because of the presence of any other species, but on their own they will create these kind of dipoles because of the electronic movements, right? So that is the first method, right? Instantaneous dipoles can be made due to the movement of electrons even without a presence of external field, right? At the other instance, what will happen? At the other instance, this electron density could come to this conformation as well, so that at the other moment the dipoles will disappear. So these are referred to as instantaneous dipoles. At some other instance, the electron density could travel towards this side, right? Electron density could travel towards left side as well. More density here. Very less density at here. So likewise, you can create some instantaneous dipoles. Right? This is also a instantaneous dipole. Actually, these are also referred to as induced dipoles, right? So at the other point, those will disappear, right? So this is one way of making induced dipoles because of the movement of electrons inside your chemical species, right? So that non-polar species can get some poles appearing ultimately, right? Okay. Second method of producing induced dipoles, that is due to the attraction of electrons or repulsions of electrons in the presence of external electric fields, right? So instantaneous dipoles or induced dipoles could appear in the presence of external electric field. In the presence of external electric fields also, these induced dipoles could appear. That idea is very clear now. We had discussed that thing again and again now. It's like this now. So if you had a symmetric electron density like this, right? If you had some electron density like this, symmetric, and if you are to apply some positive pole here, what will happen? These electron densities will move towards this positive pole and repel from these ones also move towards this positive pole, right? If you apply some negative pole here, these densities will repel from that, moving towards this positive pole. So ultimately, you will end up with some this kind of ultimate particle where you have very less amount of electrons here and very high amount of electrons at this corner, right? So negative pole will be created here and some positive pole here due to the presence of external electric field. Due to the presence of external electric field, you could come up with induced dipoles. If you remove this field, that dipole will disappear, giving you the symmetric electron density again, right? So that these are referred to as induced dipoles, right? So if you apply the electric field, the dipoles will induced. If you remove the electric field, the dipoles will disappear. So these are referred to as induced dipoles. See, these are two methods where the induced dipoles are produced because of the movement of electrons inside your molecules. One instance, there could be a phase where you have more electrons at one corner and less electrons at the other corner. So dipoles will be created. At the other instance, the poles may exchange or disappear, right? That is one way. The second way is in the presence of external electric field, the poles may induce, and if you remove the field, poles will disappear. That is why actually those are referred to as induced dipoles. Dipoles are induced. Permanently there is no dipoles, but dipoles are induced. Right now? Okay, that is the idea. So these are the two methods you can come up with induced dipoles. Right? If you think of this method, if you think of this method of creating induced dipoles, actually not only the non-polar stuff, even the polar molecules can induce this kind of dipoles. Even the polar molecules can induce this kind of dipoles. Let's discuss about that thing. How come the polar molecules can induce dipoles? See, not only the non-polar species, but also polar molecules can induce dipoles. See, how come? Let's consider the HCl molecule, which is permanent dipole, HCl. HCl is referred to as a permanent dipole, right? You have greater electron density at the Cel's corner and less electron density at the hydrogen's corner. So this is how the HCl appears. More electron density at the Cel's corner and less electron density at the hydrogen's corner. This is a polar molecule, right? This is a polar molecule, right? When another polar molecule comes closer to this thing, when another HCl molecule, let's say, when another HCl molecule comes closer to this first HCl molecule, right, like this, when the polar molecule, where the chlorine is with the negative charge and the hydrogen is with the positive charge, right? So what will happen? Towards this positive charge, right? Towards this positive charge, some of the electrons at here will attract. Towards in the presence of this positive charge, some of the electrons of this HCl molecule will attract, right? If you are to get rid of this molecule, that kind of attraction won't appear. But in the presence of this thing, some electron density of this HCl molecule will attract towards this positive pole, so that it will create some induced dipole. It will create some induced dipole. Because of the presence of this thing, some of the electron densities come towards that pole. So, induced dipoles. The same thing happens with this one as well. In the presence of this negative pole, some of the electron densities from here will repel. In the presence of this negative pole, some of the electron density here will repel, creating a induced dipole there as well. Here as well, towards this positive pole, these will attract. So like that, even in the polar molecules, these kind of small charge representations could occur. Dipoles could induce. When you remove this guy from the vicinity of this thing, these poles will be removed. That is what we refer to as kind of an induced dipole. In the presence of kind of a field, the dipoles are induced. When that guy is absent, no longer dipoles will appear. Induced dipoles. So, when regarding the connectivity of HCl molecules, the secondary interaction among HCl molecules which bound together, we could see the presence of dipole-dipole interactions, as well as the London forces coming from the induced dipoles. See? So, we can conclude between any two molecules, London forces may appear. Right? Not only between the non-polar molecules, but also between polar molecules as well. The London force will appear. Right? Because of these induced dipoles create in the vicinity of outer charges. Right now? Let's go to your note. It is written here. Right? So, at your note, these points are there. See? So, induced dipoles can be created by any polar or non-polar species, and therefore London dispersion forces are there between any kind of molecular species, polar or non-polar. The idea is clear. So between any kind of two molecules, the London forces appear. Right now? Okay. Next one. Next session under the London forces. So actually, Lamai, there are two factors. There are two factors, right, governs the strength of the London force. The strength of the London force depends on two factors, right? Let's discuss about those. Strength of London force or London forces depend on two factors. Let's discuss one by one. The first factor, the molecular weight. Molecular weight. Molecular weight. Let's discuss how this molecular weight affects the strength of the London force. How this thing affects the strength of London force. The idea is this, Lama. The idea is this. When the molecular weight is high, is considered as MW. When the molecular weight is high, what happens? The molecular weight is high means you have more number of protons in your molecular nucleus. That means you have more number of electronic shells in your molecules. That makes your molecule a larger one. So when the molecular weight is high, your molecule is larger. The size of the molecule becomes high. Size of molecule becomes high. When the molecular weight is high, the size of the molecule becomes high. Right? When the size of the molecule is high, that means your outer electronic shell of your molecule is far away from your molecular nucleus. Right? That means, as the molecule is high, means your outer electronic shell is far away from molecular nucleus. Right? The idea is clear, no? Not like a smaller species, right? When you are with a larger species, right? Where the molecular weight is high, this one is with a greater molecular weight, this one is a lower molecular weight, then your outer electron density is far away from your nucleus. So that these guys will tend to respond more to the outer charges. As these electron densities are not that much stick together to the nucleus, not that much bound to the nucleus, these will respond to the outer charges easily compared to this one. As this is a small size molecule, the electron cloud is more attracted towards its nucleus. So that electron density is not that much keen to respond to outer charges. But here, the opposite. So that when the outer electron shell is far away from your nucleus, that will respond more to the outer charges. Response more to outer charges. That means your polarizability is high, it is easy to create poles, and your London force strength will be high. As you respond more to the outer charges, you will create poles more easily. You will create poles more easily. So poles will be created more easily as you have with some greater polarizing power. Sorry, polarizability. You have with some greater polarizability. In the size is high, greater polarizability. But with this one, some smaller polarizability. Size is small, polarizability is small. Right, very negligible kind of poles will appear. Right, so here the polarizability is high with the greater size. Right, so polarizability is high, so the positive delta and negative charges will be more pronounced there. Right, magnitude of delta and negative delta are high. That will ultimately come up with some greater London force strength. It will ultimately lead to a greater London force strength. Right, so that London strength is high. Right now, that is what happens. So when the molecular weight is high, size of the molecule is high. The outer electron shells resides far away from your molecular nucleus. So those electron densities will respond heavily towards outer charges, making some greater positive and negative poles, so that the attraction between the positive and negative poles will be greater when you are larger. Right, that is how the molecular weight affects the London force strength. We can ultimately conclude when the molecular weight is high, London force strength is high. Right, that is the ultimate idea. When the molecular weight is high, London strength is high. Right now, this is the first fact, right, which affects the London force strength, the molecular weight. Right, molecular weight. Let's come up with some example. Let's come up with some example for this one. Right, see this example. So if you are thinking of let's compare these two guys, neon and argon. Neon is kind of a smaller species. Neon is kind of a smaller particle. Neon, two neon molecules. Right, so as their molecular nucleus is close to its outermost shell, those will polarize. Right, very little, like this. Actually polarizability is low when the size is small. When the size is small, polarizability is low. Right, size is small, so when size is small, so polarizability is small. Right, that is what happens when molecular weight is low. Right, so let's compare this thing with argon. Argon is much larger species. Right, argon is much larger species. Right, so when these two guys are attracted to each other, they will create some greater poles. as those guys are with some greater polarizability. Those guys are with some greater polarizability. Some poles with great positive charge will be formed here as well as negative charge. This delta is greater than this. Right? This is because when molecular weight is high, your size is high, that means your polarizability is high. So you will get some greater poles. So that the attraction between, compared to the attraction between these two guys, the attraction between these two guys are more heavy, because this is kind of attraction between some two greater charges compared to here. So the London force strength here is low compared to the London strength here. See, this kind of example, right now. So compared to this London force is more stronger. So this is how the molecular weight affects the London force strength, right? You can say that when the molecular weight is high, the size of the stuff is high, so your polarizability is high. That means you will create some greater positive and negative poles with greater magnitude, so that they will attract heavily compared to a situation like this. So when the molecular weight is high, London force strength is high. That's it, right? Second factor. Let's come up with the second factor. Right. There are two factors affecting the London force strength. Let's discuss about the second factor. Right. Second factor affecting London force strength is known as the contacting surface area. Contacting surface area. Let's discuss about that thing. Number two is contacting surface area. See how this affects. See how this affects to London force strength. The idea is this. Right. Let's come up with the example. With this example, we'll discuss the effect of contacting surface area towards the strength of the London force. Right. It's like this. Let's consider these two situations. Let's consider the pentane. Let's consider the pentane and the neopentane like this. This is pentane. This pentane molecule, right? Then you have the neopentane. Right? Then you have the neopentane. This is the neopentane. This is neopentane. Actually, both of these molecules carry the same molecular formula. Both of these molecules carry the same molecular formula. This is C5 H2L pentane. This is referred to as, this is also C5 H2L, but this is referred to as the neopentane. neopentane, or sometimes it is also referred to as 2,2-dimethylpropane. 2,2-dimethylpropane or the neopentane, right? Let's discuss about the London forces here. So basically, when it comes to surface area, this is the surface area of the pentane molecule, right? Even though it's a 2D picture, we can denote the surface area of the pentane like this. And surface area of this thing, neopentane, it looks like this. This is the surface area of neopentane. Na? Surface area of neopentane looks like this. This is the surface area, right? So actually, when it comes to surface area, this guy is with a greater surface area than this, right? This guy is with a greater surface area than this. You clearly see, no? Surface area of this thing is greater than this, right? So surface area is higher here. But what matters for the London force strength is not the surface area, but the contacting surface area. Contacting surface area. This wording is very important. Contacting surface area. Contacting surface area. See what this means. Contacting surface area, or one can say the effective surface area. See, it is like this now. So, if this guy is to connect with other C2H5, other pentane molecules, if this guy is to connect with other pentane molecules, this guy can use all of its surface area, to make some interactions, right, with the other pentane molecules. It is like this, no? If you take this one, if you take these kind of molecules, I'll draw it simply, small nature. The pitch is like this, the pitch is just like this, no? The pentane. That pentane can connect with other pentane molecules like this. This is another pentane molecule. This is another pentane molecule. So this pentane molecule can connect with other pentane molecules, right? Using all of its surface area actually, right? With the use of its all the surface area. See, with the use of its almost all the surface area, with the use of almost all the surface area here, it can make bonds with other pentane molecules. See, can connect the other pentane molecules with the use of almost all its surface area here. See, here as well, right? It can connect to the other pentane molecules with the use of all of its surface area. So as the contacting surface area, we can take the total surface area of the pentane molecule. So the contacting surface area of pentane is like this. You can take the total surface area of pentane as the contacting surface area. Right? But when it comes to neopentane, the neopentane molecule is like this, no, Laman? I am drawing it simply. That guy is just like this, no? Right? To connect with other neopentane molecules like this, you see? To connect with other neopentane molecules, Even like this, no? This guy can't use all of its surface area. You clearly see to connect with other pentane molecules. This guy can use only this surface area. You see? Not all the surface area is available. Actually, with the use of these areas, you can't connect to other molecules. So London interactions can't be made by these areas. Even though to the effective surface area, it counts, but for the conducting surface area, these areas won't count, right? So the effective surface area of these neopentane molecules are like this. As the effective or the conducting surface area, we can take only this. This area. To connect to other neopentane molecules, only this area can be used. Conducting surface area is like this. So when we are thinking of the conducting surface area, this guy wins. This guy wins, right? Even though the surface area, the surface area is high with the neopentane, but the conducting surface area is high with the pentane. So the conducting surface area, that is what matters, right? So the conducting surface area is high with this one. Conducting surface area is high here, but the conducting surface area is low here. Right? So more the conducting surface area, more London forces, more London interactions can be made so that the London force strength will be high. So with the pentane, you will see the greater London forces than the neopentane, right? That is the idea. So when conducting surface area is high, when the conducting surface area is high, you can create more London interactions can be created. Interactions can be made. That is the idea, right? That is the idea. Okay. When conducting surface area is high, more London interactions can be made so that the London force strength will be high in such an instance. So London force strength will be high when the conducting surface area is high, right? When the conducting surface area is high. So we can summarize the effect like this. When the conducting surface area is high, London force strength is high, right? London force strength is high. So that is the idea. So ultimately, as the practical observation, they have seen the melting point of this thing is actually greater than this one. When they are carrying out the melting point experiments, the melting point of this thing was like 36 0.1 Celsius, but melting point of this thing was like 9 Celsius. So that practical observation also proves that these particles are connected via some strong London forces than these. Right? These things are connected via some strong London forces than this. Right now? Okay? So this is some practical observation. So our theory matches with the practical observation. Right now? Actually, these are the two factors which affect the London force strength. The first thing was molecular weight. When the molecular weight is high, the London force strength is high. The second thing is the effective surface area. When the effective surface area is high, London force strength is high. So that you would observe some greater melting points with species with greater effective surface area. Right? Okay, those are the two facts. Right. So that is the end of the discussion with the London forces. Right? It's the end of discussion with the London forces. Let's now discuss about the relative strengths of these secondary interactions. Right? Now we have completed discussions of all the 5 types of secondary interactions. Let's discuss about the relative strengths of these 5 kinds. Relative strengths of 5 kinds of secondary interactions. Let's discuss about that thing. Relative strengths of secondary interactions. Relative strengths of secondary interactions. Right. It is like this. So basically, among your particles, if the charges are heavy, if the opposite charges are heavy among your particles, those will attract heavily to each other. That means if the positive charge and the negative charge between the particles which interact, which attract together, are with some greater magnitude, then those particles will be attracted heavily to each other, so that the strength of the second interaction will be heavy when the positive and the negative charges are heavy with the particles which attract to each other. That is the simple idea here. So that as ions carrying some complete charges compared to dipoles and induced dipoles, ions carry some complete charges, plus ones, plus twos, plus minus one, minus twos, like that. Ions carry some complete charges. When it comes to induced dipoles and dipoles, they carry some delta charges, some smaller charges. So that when an ion is involved, in your secondary interaction, as those guys are carrying some complete charges, those will attract, or the attraction they make with the other molecule will be greater. Right? So when the ions are there in your secondary interaction, you are coming up with a somewhat stronger kind of secondary interaction, right, compared to the other kinds. That is the first idea, right? After that, we can think of how the induced dipoles as well as dipoles vary in their secondary interaction strength. When it comes to dipoles, those are with permanent charges, permanent delta values, permanent charges. So their charges are actually more stronger than those induced charges in induced dipoles. In induced dipoles, slightly positive degree charges are created at one instance, and at the other instance, those will disappear or those will change their polarity. So to instance like that, compared to instance like that, the dipoles which carry some permanent charges are coming up with some greater magnitude of charge. So after the ion involvements, the dipole involvement coming up with some greater strength than the situations only involve induced dipoles. Right? That is the idea. And among the dipole interactions, the hydrogen bonds are going to be the best ones. We have learned that thing at the last class. Right? So taking all of these into account, we can conclude the interaction strength variation like this. So the most stronger second interaction kind is actually ion dipole interactions. Those are coming up with the strongest attractions. Then that your hydrogen bonds are actually with a lesser strength than the ion dipole interactions. Right? After the hydrogen bonds, next guys are the other kind of dipole-dipole interactions, other than the hydrogen bonds. Right? I write it as dp-dp, dipole-dipole interactions. And when you are involving induced dipoles, those are with much more lesser strength than dipole-dipole. The least strength is with London dispersion pulses. Which are actually the interactions between induced dipoles and induced dipole. Right? This is the idea. This is how the strength of second interactions vary. This is how the strength of second interactions vary. Right now? Strength of second interactions vary like this. Idea is clear? When you are with a total charge, that guy will attract heavily the other charge particle, no? Heavily the other charge particle. Right? That is the idea. Negative pole will be attract heavy, so the strength is greatest here. Right? Okay. And the strength will be least here. And the ions are involved. As you are with the greatest charge, right? The attraction is heavy. That is the idea. Right? This is how the interaction strengths vary among second interactions. Right now? The stuff is clear? Right. Then let's move to discuss about the melting points of molecular species. Let's discuss about that thing. Right? Actually, what this melting point means, first of all, discuss about that thing a bit. What this means, the melting point. Melting point is actually the temperature needed to convert a solid to a liquid. To convert a solid to a liquid, the temperature needed to supply is known as the melting point. That is the simplest definition for the melting point. Right? Let's discuss what will happen when a solid converts to a liquid by absorbing the temperature, the heat. Actually, what happens is when a solid converts to a liquid, the closely packed particles in a solid will move apart from each other to come up as a liquid. So in a solid, the particles are very closely packed. In a liquid, the guys are a bit away from each other. So with the temperature you provided to melt the substance, what you are doing is actually you are trying to put the particles apart from each other, from a solid to a liquid. Right? So they are to put the particles apart from each other. Actually, you have to do two things. That means to convert a solid to a liquid, or in other words, to put the particles apart from each other. Actually, you need to do two things. The first thing is actually, right, this is how the solids appearing, right? So this is the nature of solid. The particles are very closely packed. When it comes to liquid, particles are bit away from each other. Compared to solid, the particles are a bit away from each other. Right? So when converting the solid to a liquid, what you should do? You have to break this bond. You have to break this bond. That is one thing. You have to break this bond. That is one thing. And you have to move these particles apart from each other. That is second thing. Basically, actually, moving these particles apart from each other will break the bond, right? Okay. Anyway, the supplied heat is used for these two things: moving the particles apart from each other and breaking the bond. The two things. Right? Two things. Moving the particles apart from each other and breaking the bonds. Right? To convert solid to a liquid. That is what melting means. At the melting point, this is what happens, right? At the melting point, this is what happens. Right? Okay. To move these particles apart from each other, the weight matters. The weight matters. Right? If the weight of these particles are very high, to move them, you need to supply greater kinetic energy as greater thermal energy. So kinetic energy will be increased as you supply more thermal energy to the system. The thermal energy will be supplied by the temperature. So you need some high temperature to move the particles if you are with a greater weight. Right? That is the idea. The first thing, to move the particles apart from each other, the molecular weight matters. Molecular weight matters. Molecular weight matters. So when the molecular weight is high, when the molecular weight is high of your molecules, it is hard to move the particles apart from each other. It is hard to move the particles. So you need to supply great amount of heat energy to move them. Greater amount of heat needed to do the thermal motions so that your melting points will be high. Your melting points will be high. Melting as well as the boiling, right? So in this case, I am referring to the melting point. So your melting points will be high. When the molecular weight is high, great amount of heat is needed to do the thermal motions to move the particles. So that heat energy should be supplied as temperature. So your melting point is high. Higher temperatures are needed to move the particles apart from each other to melt the solid to a liquid. Right? That is how the molecular weight matters. The second fact matters with the melting points is actually the strength of bonds, strength of interactions, strength of second interaction, strength of second interaction, strength of second interaction. Or the strength of intermolecular force, right? Strength of second interaction means intermolecular force, intermolecular bond strength, right? Okay. When the strength of second interaction is high, strength of interaction is high, when the strength of interaction is high, great amount of heat should be supplied to break the bond. Great amount of heat should be supplied to break the bond. Without breaking the bond, you can't put the particles apart from each other, right? So without breaking the bond, you can't melt the substance then. So when the strength of interaction is high, you need to supply greater heat to break this bond, right? So great amount of heat needed to break the bond. So that means you need to supply great amount of heat so that you need to supply some greater temperature. So your melting points will be high there. When your second interaction strength is high, your melting point becomes high. Right? So actually, when we regard into melting points of molecular species, when we are trying to compare the melting points of molecular species, right? These two things matter. The ones with greater molecular weights will have some greater melting points as well as greater boiling points as well. If you are need to convert this thing to gas, see the same, right? Liquid turns to gas, this is a boiling point. That is also the same scenario, right? When the molecular weight is high, so your melting points and boiling points are high. And the second thing is when the strength of interactions is high between the particles, your melting points or boiling points are high, right? Those are two things govern the melting points and the boiling points of molecular species, right? Let's consider some examples. This is the first example. See, it is appearing in your note, right? The example number 1. It says Br2 and ICl are isoelectronic. Br2 and ICl are isoelectronic. But it says Br2 boils at 59 Celsius and ICl boils at 97 Celsius. Let's try to explain this statement, or let's try to explain this observation. Right? Br2 and ICl are isoelectronic. Isoelectronic means these two guys are with same number of electrons. same number of electrons. If you are dealing with same number of electrons, one can say their molecular weights are closely similar. Molecular weights are not that much of a difference. So the number of electrons means same number of protons will appear at the molecular nucleus. That means almost same kind of a weight will be there, right? So that you can say as same number of electrons are appearing, molecular weights are closely similar. So for this kind of a situation, what matters for the boiling points is actually the second interaction strength. The second interaction strength. I earlier said no, there are two things matter, no, molecular weight or the second interaction strength. So in this case, what matters should be the second interaction strength. We'll compare with the second interaction strength, right? Okay. When it comes to second interaction strength, first of all, we have to identify which kind of interactions appearing between the Br2 molecules as well as ICl molecules. If we are able to come up with the second interaction type, then we can compare. As we know, the ion dipole are the strongest, as well as the weakest are the London, and we know the variation, which second interaction is with a greater strength and which is with a smaller strength. So as we know the variation, we can comment if we know about the type of second interaction appearing between the Br2 and ICl. Let's come up with that. To discuss about the type of interaction, come up with the type of interactions, first we need to know about whether the particles are polar or non-polar. If your particles are polar, between polar particles, which are referred to as dipoles, dipole-dipole interaction may occur. If your particles are non-polar, which are referred to as induced dipoles, the induced dipole interactions or the London forces may occur. If you are with kind of ion dipole or ion induced dipole interaction may occur. So first of all, you have to identify whether the particles are polar or non-polar to comment on the interaction kind. Let's do that exercise, right? So we can write as the first point the Br2. Br2 is kind of non-polar species, and the ICl, as you are with some difference between the two guys, ICl is kind of polar species. The electrons will be attracted towards the Cl, but here it is non-polar. So first point you have to write is the Br2 is a non-polar molecule while ICl is a polar molecule. ICl is a polar molecule. So among Br2 molecules, among non-polar molecules, only the induced dipole interaction, that means the London forces appear. So we can write among Br2 molecules, only the London forces appear. And among ICl molecules, dipole interactions, polar molecule dipole interactions as well as London forces appear. Among all the kind of molecules, London forces are there, right? Okay. So among ICl molecules, dipole interactions and London forces appear. Right, these are the marking points, right? So we have to first identify whether the guys are polar or non-polar. These are the marking points, right? I just mark. Then among Br2 molecules, only London forces. And ICl molecules, dipole-dipole interactions, and London forces. 2 marking points are there. Right? Then we can say the dipole-dipole interactions are stronger than London forces. You know, as we know, the dipole-dipole things are stronger than London forces. No, well, we have learned. No, so we can say secondary interaction strength. Secondary interaction strength of dipole-dipole interactions are greater than London forces. Right? No? So that we can say as the secondary strength is greater with ICl molecules, ICl is with a greater melting point. That is what you observe. Greater melting and boiling points. That is what you observe. So boiling point variation should be with ICl winning. Right, ICl winning. Right, beating the Br2. Right now? So that is the idea. That is the idea. Right? This is how you're supposed to complete an answer. All the marking points should be written. These are the marking points, right? So this is the idea. All the things should be written correctly. This is how we use, right, the factors affecting the melting points to describe these observations. Right now? Okay, let's come up with another example. Let's come up with another example. Another one. Example number 2. Example number 2. Although molecular weight of H2O is lower than H2S, boiling point of H2O is higher than, actually boiling point of H2O is 100 Celsius, no? It is higher than that of H2S. This kind of observation, practical observation. Let's try to explain this one. Let's try to explain this one with the use of our knowledge we gathered these 2 days. Right? So what we can say? So they are clearly saying that molecular weight of H2O is lower than the H2S. Boiling point is greater in H2O. That is the idea. So first of all, before commenting on this one, I'll give you some little idea here. Actually, which factor to consider or which factor wins, whether the molecular weight or the second interaction strength, which will win when designing the boiling point. In this case, what we see is with the molecular weight, the H2S wins. With the molecular weight, the H2S wins. But with the interaction strength, we know H2O with hydrogen bonding. H2S is with dipole. With the interaction strength, we clearly see the H2O wins. With the molecular weight, the H2S wins. With the interaction strength, H2O wins. But the ultimate observation was a win for the H2O. How we decide? How to decide? Right? Which factor to consider? Commenting on the melting points. Right? Whether to consider the molecular weight factor or whether to consider the second interaction factor. We may come up with some confusing thing here. Let's try to solve that thing. Right? This is the thing is this, Lama. This is the idea here. Right? So when this kind of thing appears, what was the problem here? The problem is, right? We know that when the molecular weight is high, right, boiling point should be high. But here, even the molecular weight is high with the H2S, the boiling point is low with that. Because not the molecular weight factor, the other factor considered here. The second interaction strength. Let's discuss how to resolve that confusion. Right? The idea is this, Lama. So when we are trying to come up with the molecular weight, that decision, when you trying to come up with the melting point, that decision, right? This is how you need to look at the situation, right? So first consider the molecular weight, right? So, and if the delta MV, the molecular weight difference, if the molecular weight difference is actually greater than 50 units, if the molecular weight difference is greater than 50 units, normally this could be applied. If the molecular weight is greater than 50 units, the molecular weight factor wins, and it will be the one to decide the melting point. Then with the species with greater molecular weight is with the greater melting point or greater boiling point. Right? That is the idea. But if delta MB, the molecular weight difference is less than 50 units, roughly, less than 50 units, then we can consider the molecular weight is more or less the same. We can consider molecular weight is the more or less the same. So we can consider that, right? That is okay. So then we say the one with the secondary interaction strength with some higher second interaction strength will have the greater melting point or greater boiling point. This is how we decide. Right? It's very important. Huh? It's very important for this kind of problems, to answer this kind of problem, or predict the things correctly, the melting points or boiling point variation correctly. This is very important. Right? This is very important. So if the molecular weight difference is greater than 50 units, according to the molecular weight, we decide the melting point. If the molecular weight difference is less than 50 units, according to second interaction strength, we decide the melting points. When it comes to this scenario, when it comes to this point, these two guys, actual molecular weight of this thing, H2O, is equal to 18. Molecular weight is equal to 18 for the H2O. Oxygen 16, hydrogen 1, 2 of those, 18. Molecular weight of H2S here is actually equal to 34. Sulfur carrier is 32 and 2 of hydrogens, it is 34. So if you think of these two guys, the molecular weight difference is less than 50 units. Is less than 50 units. So the H2O H2S, that comparison comes with this form. Molecular difference is less than 50 units. So that second interaction strength matters, not the molecular weight. So with this thing, we are able to comment which one will carry the greater boiling point. Right? As you know, among H2O molecules, the hydrogen bonds are there. Among H2S molecules, you have the dipole-dipole interactions, as it's a polar molecule. The hydrogen bonds are stronger than dipole-dipole interactions, so that the water should be greater than the second interaction strength, greater will be the boiling point. Right now, that is how we are supposed to comment on this kind of stuff. Right? Okay. So let's write the points here. Let's write the points, complete points here to explain this one. Right? Okay. Right. These are the points. First point. So here we are considering some more or less the same molecular weight situation, right? Okay. Less than 50 units. So what matters is the second interaction strength. So if you are commenting on the boiling points or the melting points according to second interaction strength, first you need to come up with the polarity of the stuff, because those are the ones, the polarity of the stuff is the one which decide the interaction kind, right? Second interaction kind. With that only you can comment on the relative interaction strengths, right? Okay, let's come up with that. So H2O is a polar molecule as well as the H2S, no? Both, ne? H2O as well as H2S are polar molecules. Polar molecules. Right? Second point. Then what kind of interactions are possible there? Among H2O molecules, hydrogen bonds plus London forces. Among any kind of molecule, London forces are there, right? London forces present. And among H2S molecules, as polar, no? Among H2S molecules, dipole, no? Dipole, polar guys, no? Dipole interactions and London forces present to exist, right? And when it comes to second interaction strength, right? Hydrogen bonds are stronger than dipole interactions. Hydrogen bonds are stronger than dipole-dipole interactions. So that boiling point variation is with some hydrogen bonds winning here. Hydrogen bond carrying particles will win. That means H2O. H2O is with greater boiling point than H2S. This is how we are supposed to explain the observation. Right now? This conclusion was made because the molecular weight difference is not that much. So we can take the molecular weight are closely similar, so that the second interactions, the strength of second interactions will decide the melting points. Right? Okay. Let's come up with another example. Right? See, example number 3. One can write like this. This is another observation, right? Melting point melting point of I2, melting point of I2, which is a 58 Celsius, right, is greater than the melting point of H2O, which is with 0 Celsius, even though among I2 molecules only London forces appear. Whereas among H2O molecules, hydrogen bonds appear. See, even though the second interaction strength in H2O is greater than in I2, because the I2 is non-polar particle. Non-polar means only London forces are existing there. H2O carrying some hydrogen bonds. Even though the second interaction strength in H2O is greater than that of I2, still the melting point of I2 is greater than that of H2O. So for this observation, we clearly see second interaction strength is not the case. That is not matters. It is not the one who decides the melting points here. Then what? Then it should be the other factor, molecular weight. It is very clear, no? See, why is that? Because when it comes to I2, its molecular weight is 254. Molecular weight of one iodine, atomic weight of iodine is 127. We have two of those, 254. When it comes to H2O, its molecular weight is actually 18. So you clearly see this molecular weight is very higher value than this one. it is exceeding 50 units. So totally the variation then will be dependent on the molecular weight. Greater the molecular weight, greater will be the melting points. Right? That is the idea here. See, this, write the stuff here. We can write molecular weight. That is what matters, right? Here, molecular weight of I2 is 254 G mole minus 1, right? Here the 18 G mole minus 1. That value is greater than, very, very greater than H2O is 18 G mole minus 1. Right? It's very heavy. I2 molecules are very heavy. So, the thermal motions of I2 molecules are very little compared to H2O. Right? Thermal motions of I2 is very little compared to H2O. Thermal motions of I2 is very little compared to H2O. The lighter ones will move easily. The ones with greater weight, right, not that much keen to move, right? Okay. So thermal motions are very less with I2. So to move the I2 molecules, it supply greater heat. So greater heat energy should be supplied to do thermal motions. To do thermal motions in I2 compared to H2O. So even though you are with weaker second interaction, right, the melting points of I2 will be higher. Right? Melting point of I2 will be higher. So even at 25 Celsius, I2 appears as a solid. So we can write so boiling point, sorry, melting point. Variation is I2 having a greater melting point than the H2O. So if you to your knowledge, we can say I2 is a solid at room temperature. I2 is a solid at room temperature. H2 is a liquid. Right? Kinetic energy of the room temperature is not sufficient to move these I2 molecules and convert it into a liquid. Right? Kinetic energy at room temperature or the heat change at room temperature is not sufficient. Not sufficient to do molecular motions of I2 and make it a liquid. Right. That is the idea. Kinetic energy, or one can say the thermal energy, both are same. Thermal energy at room temperature is not sufficient to do molecular motions of I2 and make it a liquid. Let's see, it has better to write it as thermal energy. Both are same, right? Thermal energy at room temperature is not sufficient to do molecular motions of I2 and make it a liquid. Right? That is the idea. So you clearly see, right? If you are with some greater molecular weight difference, molecular weight is the one which decides the melting points, not the second interaction strength. Even though I2 is with London forces only, right, still it won over the H2O, which was with hydrogen bonds. Right? That is the idea. So the idea is clear, no? Right. So let's discuss another example. Right? Another one. Example number 4. Example number 4. See, this also there in your note, right? So boiling point of CH4. Boiling point of CH4, which is 164 Celsius, is lesser than that of xenon. Which is minus 108. See how we are supposed to explain this observation. Let's try to explain this observation. Boiling point of CH4 is lesser than that of xenon. Right? Okay. That's what we can do. Right? Actually, both of these guys are with London forces. If you think of the second interactions, both are non-polar. So London forces appear. Among CH4 molecules. This guy is also non-polar. So London forces appear among xenon molecules. Right here. Right? So second iteration's kind is same. Right? So we can think of London force strength here. Second iteration kind is same, but with the molecular weight, you can you can comment on the London force strength here. With that also you can come up with the answer. Or else, as xenon is with a very high molecular weight than the CH4, with that point as well you can come up with the melting points. Greater the weight, molecular weight, greater will be your melting point. So two answers are possible here. Let's write both. Right? Explanation 1. Right? One can write like this. depending on the molecular weight. Depending on the molecular weight. Explanation 1. Right? You can write like this. Molecular weight. Because molecular weight, right? CH4 is very, very small than the xenon. Right? Xenon appearing at the 6th or 7th row. Right? Bottom of the periodic table. So having a greater mass there. So thermal motions are very less in xenon. Very less in xenon. So greater heat or greater thermal energy should be provided to the thermal motions. Of xenon, the motions of xenon particles compared to CH4. So to do such, to provide such kind of a greater thermal energy, you need to supply greater heat, greater temperature. So the boiling point. The boiling point of xenon will be high. That is explanation 1. The use of molecular weight, just the molecular weight. Right? If one is trying to explain the same idea, right, with the use of London force strength, right, you can come up with this kind of answer. Right? Here, what we are doing is using strength of London forces. To describe the observation. Right? If you are going through that pathway, you can write like this. First, you can write both the CH4 and Xe are nonpolar. Both CH4 and Xe, xenon, are nonpolar. So among CH4 as well as xenon particles, only London forces exist. Which as well as Xe particles, only London forces exist. Then we can write the molecular weight. Molecular weight of CH4 is less than that of xenon. So what we know is when the molecular weight is high, London force strength is high. When the molecular weight is high, London for strength is high. So that you can say that xenon is with some greater boiling point than CH4. Right now? So that is the idea. So like that also you can explain the same observation. Now this is the best explanation, or one can come up with this kind of explanation as well using the strength of London forces, as both are with the same kind of interactions, and London forces strength varies according to molecular weight. Anyway, molecular weight was the major fact governing uh, this boiling point variation, right now. So this is the fourth type of this is the fourth example what we have discussed with the melting point variation, right now. Okay, so that is all actually what we have to learn with the secondary interactions, right? With this thing, let's bind up at this stage for the secondary interactions, right? And we will have a very small discussion on the melting points at the next session, very small one, that will actually cover all the things as a quick summary of what we have learned with the primary as well as secondary interactions, right? Okay, then see you until then. Goodbye.